All right, Prop 47 says, in right-angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle. So this is the Pythagorean theorem. So right-angled triangles, the square on the side subtending the right angle, which means kind of like the side that is opposite the right angle or the hypotenuse, is equal to the sum of the squares of the other two legs. Okay, so let's prove this. The very first thing is that we'll stand up squares on each of these. Right, so I think I can just jump straight into the proof. I guess this is just part of like the setup, but it's written in here to construct the squares. So construct squares. How should I say? Construct the squares on AB, BC, and CA. And that was just the very last proposition. Standing up some squares. Okay, so that's just like the setup. And I've already kind of put my squares in here in pencil. I'll just come through and set them up now. Okay. And it's a pretty quick proof now that we've got so many propositions all set up. All right. Almost there. So I'll make these squares, I'll label them, and then we'll get a move on. Yeah, that's a nice little diagram. Okay, we'll call this A, B, F, G. Over here will be B, D, E, C, and then C, K, H, A. There we go. It's a little bit smudgy. Get out of here. Some strange pop-up. Okay, so there's our squares. A little bit more to be done before we just jump straight into the proving. So next, through A, let AL be drawn parallel to either BD or CE. So we're drawing a line through A parallel to BD. And where it intersects over here with ED, we're going to call that point L. So let's see, I'll just kind of eyeball this. That looks pretty parallel to me. Put it in as dashed line so things don't get too muddied up. Okay, and we call this point L. So construct let's see, I'll just say construct AL parallel to BD, just to keep it short. And that was prop. Let's see, that's not cited in my book. I would like to cite it. It's making a parallel line. All right, which one was that? Through a given point to draw. Yeah, prop 31. There we go. Not that important, but I felt like it should be cited. Okay, there we go. And then join AD and FC. That's not bad. Come on, cooperate. Cooperate with me, papers. AD. So just getting the setup still. AD and FC. Yeah, here we go. Maybe just based off of these, maybe you can kind of see the tactic. Can you see it? Well, the tactic is going to be that we have this triangle right here, ABD, which looks real similar to CFB. So we're going to do something with those. What do we do? All right, so since angles BAC, BAG are right, so BAC and BAG, and that's just by construction. Since this is a right-angled triangle and then this is a square, we constructed that as a square. So since that, and I'll just mention both are right, although I don't think that's quite as important. Let's see though. It follows that with straight line BA and at the point A on it, the two straight lines ACAG not lying on the same side make the adjacent angles equal to two right angles. Oh, okay, it is important that they're right. Therefore, CA is in a straight line with AG. Yeah, so right. So basically, since BAC and BAG, those two angles are two right angles, we have a proposition that says the line CG is a straight line. So I'll just say CG is a straight line. And that was what was that? Prop 14. It tells us that. Okay, and for the same reason, similarly, BA is in a straight line with AH, so BH is a straight line. Okay, and since the angle DBC is equal to FBA, so DBC equals FBA, because they're both corners of a square, they're both right. If we add ABC to each, then the resulting sums are equal. So we'll just say, then note, angle DBC equals angle FBA by construction. So adding ABC to both sides, angle ABC plus angle DBC equals angle ABC plus angle FBA. Okay, but let's look at that. So ABC is right here plus DBC. Well, that forms DBA. And ABC with FBA forms FBC. So angle DBA equals angle FBC. That's just common notion that gives us that. All right, well, since DB equals BC and FB equals BA, so DB is equal to BC and FB is equal to BA, we get that triangle ABD equals triangle FBC by side angle side, prop 4. So, okay, well, that's pretty clever. That's kind of where we thought we were going, but how is that going to help us? Well, just a quick look, ABD, let's see, ABD is this right here. And notice that ABD falls between the parallels BD and AL, and it shares a base with the parallelogram BL. So this little sort of, I guess it's a rectangle right here, shares a base, BD, with ABD, and it falls in the same parallels, which means that BL is twice ABD. So I guess I might say, since BD is parallel to AL, we get that triangle. Should I say, yeah, I should say, rather than saying the triangle is half of the parallelogram, I should say the parallelogram is double the triangle. Okay. BL, I'll just call it BL, it's a parallelogram, is 2 times triangle ABD. And that was, what proposition was that? 41. Yeah, so the parallelogram BL is double the triangle ABD because they have the same base. For the same reason or similar reasons, we would get something going on here with triangle FBC and the square AGFB, because again, they fall between parallels AG and BF. They share a base, BF. So yeah, this square AGFB is 2 times FBC. So let's see, I think we'll call it GB. Square GB is 2 times triangle FBC. But we already pointed out that FBC and I called it DBA. Oh, no, here I called it ABD. Yeah, so FBC is equal to triangle ABD. And here's a line that is kind of put in. It's in brackets, which means that it wasn't originally there when Euclid wrote this, but it has been added. But the doubles of equals are equal to one another. So in other words, we get that GB is equal to BL. Let's see. Right, and I guess I should have stated this is also prop 41, but it's just back to back, and I think it's pretty obvious. So yeah, GB is equal to BL. Let's see, and then it's going to be a similar argument, because what we've proven now is we've proven that GB, the bottom square, is equal to like the smaller piece of this rectangle. We're going to go through, or we would go through, use a really similar argument to prove that HC is equal to the top part of this. I guess maybe you could call it CL, so that the sum of these two squares is equal to exactly that square. That's the idea. So we'll just kind of write that line. It's basically just a one-liner. So by joining, let's see, what do we join? AE, BK, and I need a second page. So, and I won't join them, but joining AE and BK, we can show similarly show that, let's see, what does he say? So if AE and BK are joined, the parallelogram CL can be proved to be equal to HC. Yeah, so we can show CL equals HC. What does he say? Therefore, the whole square BDEC is equal to the two squares GB and HC. And that's pretty much it. So BDEC equals GB plus HC. And that was what we wanted to prove. Cool. Pythagorean theorem is done. QED. therefore, etc.